We continue where I stopped last week, namely I ended last week with the discussion of the problems of deductivism, and you may remember, and I'm sure you do, that I discussed the problems of deductivism, especially that derived from the fact that we don't have in deductivism a principle for the acceptance of theories. So we do have principles, or rather freedom, for the generation of theories and hypotheses and the like, because in deductivism we are free to invent theories, hypotheses, as long as they are in principle falsifiable, and then we are obliged to test these as thoroughly as possible by deducing predictions from them and then comparing these predictions with empirical data. But the fact is that we get the order from deductivism to keep testing. And we have no way to say, now, for the moment, it's enough with testing, and now we want to apply it, the hypothesis, the law, or whatever it is, or the model, because we have no justification to stop testing. And there are always infinitely many possibilities of testing a hypothesis, because whatever you state, whatever the connection is you're stating, there's always the possibility that the variable you're interested in depends on many other variables as well, which you haven't tested yet. And it may depend on the rest of the universe. So you have no way of stopping testing with respect to everything that happens in the universe. So we have no way of coming to the application of hypotheses of general laws or theories, application be it within science for explanation and prediction or outside of science for technical applications. This is a major problem for deductivism, and the whole idea of criticism, which makes this basic idea of deductivism so attractive, turns out to be somehow self-destructive. Criticism is something very nice, but somewhere you must stop criticism, because otherwise it becomes self-destructive. You have no way of stopping criticism, and that means nothing stays stable, and you have no way of having a pause, so to speak, the room then to apply a hypothesis for scientific or extra-scientific purposes. So this is a major problem, and paradigm theory is one of these answers to deductivism in order to solve this problem. But in order to develop paradigm theory, we have to make, so to speak, a fresh start, because paradigm theory is not a normative philosophy of science. It is basically a descriptive philosophy of science, and that will turn out to be a major problem also for the justification of paradigm theory, but that has to wait a little until I have developed paradigm theory. Now, the point of departure, before I do that, are there any questions with regard to the criticism of deductivism that have appeared in the meantime? It's not the case. Was it comparatively clear? Yes, someone nods, someone has empty eyes. Okay. If you don't ask, I won't answer anything, right? Okay? Right. But if you don't have to ask, you don't have to ask, of course. All right. So we come to paradigm theory, and I gave you already a basic idea of paradigm theory. Rather, I started with developing the basic idea of paradigm theory, and the general idea is to compare the normative positions with the reality of science as it has emerged in the history of science. And then we'll find a strong discrepancy, which is, of course, to be expected in a sense. For instance, we do not expect, well, you probably do not expect, that we find in the history of science continuous theory testing without stopping, right? Without predictions and without applications. You know that people use scientific results for applications, So certainly people don't behave in science. Scientists do not behave the way that deductivism seems to prescribe, namely continuous testing, 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 and no stopping. Of course, that doesn't happen. Somehow people stop. The question is whether we can understand that people stop testing, because from the point of view of deductivism, it's simply forbidden. It's a normative philosophy of science. It tells you how you should behave in order to do good science. So you should not stop testing, but in fact, the fact is that, of course, in science, people stop testing. And the question then is, from the point of view of deductivism, whether that's legitimate or whether these are just bad scientists or not. Well, it can't be that they're just bad scientists because, as I said, continuous criticism, testing, 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 no end, is self-destructive in a sense because you don't get anywhere in the end. So the idea is then that paradigm theory starts somewhat all over from fresh, completely new, by being a descriptive philosophy of science, namely by describing certain aspects of the history of science, of a real science that has happened. And the discrepancy which we shall then observe between what has happened in science and what is described in the normative positions of science, this discrepancy poses a certain problem because it does not simply say, well, if there is a discrepancy, then surely the normative positions are just wrong. That could be, of course, the case, but it's certainly not a proof when I have, say, on the one side, the norms that say something, how science should be done, and then I have a scientific practice that's different from it, that only shows, well, there's something wrong, but we don't know which side is wrong. And that is what I'm going to develop now a little further, because, as I said, there are two main possibilities to explain the discrepancy between the normative philosophies of science and what can be described as real science in the history of science. Either the norms are wrong, for instance, they are unrealistic, and there must be something of that sort going on that we saw already in the problems of deductivism, because these norms cannot be fulfilled without self-destroying the whole enterprise, so there must be something wrong, but possibly that's not the full story. The other possibility is that the actual practice of science is bad. For instance, that the actual scientific practice, of course you're certainly convinced that can't be the case, but look, who knows? A critical view, perhaps, discovers that much of scientific practice isn't as good as it should be because it's dogmatic. It's just sticking to a certain point of view where deductivism would say, hey, wait a minute, you should criticize your point of view. It could be wrong, right? And you shouldn't just stick to it. That could also be the case. It could be the case that much scientific practice is dogmatic and therefore it should be criticized. That's also a possibility. We can't judge that a priori. So we must find somehow a viewpoint from which we can then judge what to do with this discrepancy between the normative philosophies of science and the actual history of science. And paradigm theory will help us in doing that. It will assess somehow these practices. And we'll find out that after the development or during the development of paradigm theory. That's what I said. From the discrepancy alone, one cannot judge whether the norms should be given up or the practice, or if the practice of science should be changed. This is just the open question. And remember, this is in general the case. Wherever that is, where you have certain norms and you have a certain practice or certain reality, and the norms and the reality do not fit, it's always open what's wrong, right? You may have a revolutionary theory of society, for instance, that tells you society, that gives you norms for society that are not fulfilled in society, for instance, norms about justice, and then you look at real society and you find, well, these norms of justice are not fulfilled. There are always two possibilities. It may be that your norms are bad, you may be convinced of them, but they may still be bad, right? They're just completely unrealistic. That's one possibility. And of course, the other possibility is your norms are okay and society is just bad by being unjust, right? That's a possibility. Or it may be a mixture of two, right? It may be that your norms you're developing, say in a radical form of whatever, communism or socialism, whatever it is, or anarchy or whatever it is, you develop certain norms and then your norms may be just, overstated and unrealistic. And society is unjust and it's also bad, right? So the discrepancy alone, that is a very general point of view one should be aware of, because usually people just make a decision, say, oh, my norms are wonderful, I'm an anarchist, and anarchy is really the best in human life, so society is so bad because there's so much orders and constraints, so we think we should criticize society. Well, perhaps you are right, but perhaps you are wrong. Perhaps your norms are just unrealistic, right? This is always an open question. Mostly people make a very quick decision in that respect. They either adhere to their norms or they defend them, for instance, society, think that's all okay. But it's just from the discrepancy, nothing follows. It just follows something is wrong, but you don't know what is wrong. And that's the same in science. One should be aware of that. And here I think a certain amount of criticism is very useful to be aware of the fact that from the discrepancy alone, nothing follows with regard to one or the other party involved here. Okay? Now, before deciding this question, that's what I'm proposing here and how I'm developing the position, before deciding the question what is going on here, whether the norms are wrong or whether the practice of science is wrong or whether both of them have deficiencies, paradigm theory aims at a description of general characteristics of science, and especially a description of the development of science over time. Right? So what we get from paradigm theory seems to be at first sight at least, a little remote from what we did so far. Because paradigm theory as a descriptive philosophy of science now aims at a general description how science develops. And you will not be able to make immediate contact from this general description, how the sciences develop, to the normative philosophies of science. So you have to be a little patient. That will come later. But it's interesting in itself, what paradigm theory tells us about the development of science, but you have to wait a little until we can make contact to the earlier philosophies of science, inductivism and deductivism. So be a little patient and just listen to what paradigm theory has to tell us about the development of the sciences. Okay, that's the framework. And what paradigm theory gives us, proposes to us, is a developmental model of science, and I'm going to tell you more precisely what that means, a developmental of science. Now, paradigm theory describes the general characteristics of the development of the basic disciplines of the natural sciences. Now, that's quite a little bit. So the general characteristics, and which general characteristics this will be, I'll show you in a second. The general characteristics of the development of the basic disciplines of the natural sciences. If you look at the natural sciences, there are basic disciplines and there are more applied disciplines. You are involved in the applied disciplines mainly. Basic disciplines are basic physics, basic chemistry, basic biology, basic geology. There are basic disciplines in the sciences, and what you do is more in the applied domains, be it in the stronger engineering domains where you apply certain results from the sciences, and you have your own developments, of course, in engineering science, or people in horticulture science, in various branches of biology, botany, also engineering, design of greenhouses, and also for economy, you are more in the applied domains of sciences. Now, what paradigm theory aims at is a description now of the development of the basic disciplines, and you will see that an understanding of the development of the basic disciplines of natural science is also very useful for an understanding of the applied disciplines where you are in, right? So that's not just useless because I'm talking about something that doesn't concern you. Of course, you did have your classes in your bachelor degree, for your bachelor degrees in the basic sciences. Of course, you learn some biology, some chemistry, some physics, and so on and so forth. Okay, so that's the basic disciplines of the natural sciences as opposed to the applied ones. It's important to know that paradigm theory mainly speaks about natural sciences and much less about the social sciences. The social sciences have different developmental patterns, often from the natural sciences, for various reasons, to which I come. And now, these general characteristics of the development of the basic sciences are described by a phase model or a developmental model. that is a model that tells you how the sciences develop. Okay? If you can't imagine anything, what that may be patient. In a second, you'll see what I mean. It's a developmental model or a phase model that tells you that the sciences typically develop in certain phases. So there will be a phase 1, and then a phase 2, and a phase 3. I'll give you the details in a second, just that you know the general picture. It says it's not a completely continuous development, such there is nothing you can distinguish in that development. But a phase model says, yes, you can distinguish certain phases. You have a phase 1, and then there's a transition, and then there's a different phase, and that phase 2 is somehow different from phase 1. It's not an absolutely continuous development where you have no differences happening in between, but there will be differences that lead to these phases. Okay, that's abstract, but you'll see it in a second. Well, that's what I just said. In such a model, different phases of a science's development are distinguished, and that temporal order is described. So we have phases in a certain order, and a phase model just describes you the succession of these different phases, describes you the phases themselves and their succession, meaning the transition. And you have to, of course, understand why there are the phases and why there are transitions, and that's exactly what I'm going to do. So that's the general way that paradigm theory gives you such a phase model, and the phase model is supposed to describe the development as it happened in history, the development of the basic disciplines of the natural sciences. That's the idea. And what we learn from them regarding the normative philosophies of science and also the mechanisms and the inner working, so to speak, of the applied sciences we'll see later. You must be patient and first understand this one, and then you'll get the point of view to approach the other problems. Okay? In each of these phases, this is now a characteristic of these phases, the practice of science is very specific. So the difference between these phases will be that the practice of science, the way science is done, is different in the different phases. Right? You may ask the question, oh, that's very strange. Science have different phases. What's their difference? Well, the difference concerns the practice of science. And you'll see immediately then, in the next, from the next slide on, what these differences between practices consist in. Okay? That's the abstract picture. If you don't really know what's going on, don't worry. It'll become concrete. When? Now. Okay. Now, first one more abstract sentence. The phase model, I'm sorry for this one, but that will become some sense. We'll get some sense, but I didn't get the temporal order on the transparency right. Okay. The phase model is a cyclical model, or more precisely, a spiral model, forget about that at the moment, of scientific development, and its structure is as follows. And here comes the structure, if my slides do what I want. Yes, it does. Oh, I bring that all together. What is the matter here? Okay, here we are. So here is the phase model. It's this one here. We have a phase P that leads to a phase N. Phase N leads to a phase R. And then phase R leads back to N, not really to the same N, but to a different N. I'll show you at the next slide. Okay. So we have 3 different phases. It's a cyclical model. Well, it's a spiral model in the sense when I go from N to R, and when I come back to N, I don't come back to the same N. I come back to a different N, right? A new N. So in a sense, we have a spiral moving, well, upwards, for instance. Okay? And here you see, I tell you why I have the letter P here. P stands for prenormal science. I know that you don't know what that is, but I have to introduce that term once, and I introduce it here. P stands for prenormal science, N stands for normal science, and R stands for revolutionary science. And I'm going to explain, of course, what prenormal science, normal science, and revolutionary science is. Okay? So that is the basic model. So paradigm theory tells us, look, if you look at the development of a basic discipline in science, say physics, a certain part of physics, say electrostatics, right? then you find the following development. You start from something which is called prenormal science in electrostatics. You don't know what that is, but that's called prenormal science. Then we'll have a certain transition to a phase that is called normal science. We get a phase of normal science in electrostatics. And for a while we have this sort of normal science in electrostatics. And then there are certain events, which I'm going to describe, that lead us from this phase of normal science to something else, namely a sort of revolutionary science. And then we'll have a phase of revolutionary science for some time. And after a while, we get another transition, namely to a phase of normal science, not back to the old normal science, but to a new phase of normal science. Okay? That's the mechanism. You don't understand what the phases mean. I'm going to explain them to you. So you see the structure here. This is apparently or obviously a phase model. We have different phases in the development of science, namely phases of prenormal science, normal science, and revolutionary science. And we have a cyclical, or more precisely, a spiral model, you know, moving upwards from P to N to R and then to another N. And to show you that a little more closely, well, that is what I told you more or less. The errors in the model should be understood as follows. From P, a first phase of normal science, N1, is reached. Then N1 reaches to a first phase of revolutionary science, R1. And from R1, a new phase of normal science, N2, is reached, which in turn leads to a new phase, R2, and so on and so forth. Okay? So it's not really something which is completely cyclical, where you come back to the old stuff and then you go somewhere else and then you come back to the old stuff. No, no, no. You come to something new, but it's again a phase of the same sort of character. The N2, the normal science N2, has the same sort of character as N1. It's all normal science, and that means there is a specific practice of science, which I'm going to describe in detail, of course, what the practice of normal science is. That's the general idea of this phase model, that we have something like, and that is, of course, sounds interesting here, phases of revolutionary science, where something revolutionary somehow is going on. And of course, I'll have to explain exactly what that means. Okay, is that a clear picture? In principle, you don't understand the details, but you should see the structure first. You have the whole picture now, and we fill in now details. The details I have to fill in is, of course, what is prenormal science, what is normal science, what is revolutionary science, and then, of course, why do we have a transition from prenormal science to normal science? Why do we have a transition from normal science to revolutionary science? Why do we have a revolutionary science to normal science transition? And what's the difference between the N1 and the N2, right? The difference between these phases of normal science, because they are not identical, they are different. So what's the difference, okay? And once you have understood all that, which takes us another 3 hours or so, then you'll have understood this phase model. And then, once we've understood this one, we can go back then to our original question and ask ourselves, what can we learn from this descriptive account of the development of the basic sciences? What can we learn from that with respect to the normative philosophies of science, which brought us into problems? All right? So that's more or less the program for what is to come. Now, I start then with prenormal science, okay, according to this program. I start with a phase of prenormal science and then tell you what's coming next, the transition then to normal science, and that's the way I developed this model. Now, prenormal science is a scientific practice which is not very structured and in which various schools compete. Just to give you an immediate example of what normal science is not, if you look at today's physics, say, classical mechanics that you've learned, or classical electrostatics, there are not various schools who compete. It's just a consensus that people know how electrostatics works. It's Coulomb's law with everything that follows from it, right? There is no disconsensus. There is a consensus. There are not various schools. So it is something which you may know from other fields, but certainly not from today's, say, school physics that you learned in your university classes for your bachelor. So, but I'll give you an example. These different schools You may know that from the social sciences. The social sciences are pretty much like this in many aspects, that you have various schools that compete, say in psychology or in sociology or political science. You have various schools. There's not just a general consensus. And it's similar to what is here called prenormal science, but I'll come back to this question. If you ask yourself what is the difference between these various schools, you'll get an example a little later, that they have fundamental viewpoints about their subject matter. So they're all dealing with a certain subject matter, but there is no consensus about the viewpoint, how you should look at that, and how you should conceptualize it. There are even disagreements about what does and what does not belong to the field. If you have a certain field of phenomena and you have different viewpoints, you may agree about certain phenomena that they belong to this field, but you may disagree about other phenomena, whether they belong to the field. Right? There is even disagreement what belongs to the field and what does not belong to the field. Now, this is pretty abstract, so I give you an example from a phase of normal science, namely research on electricity in the first half of the 18th century. I know that you don't know anything about that, unless it's your hobby to do some history of science. Okay, but I just explained to you, and it will be plausible in a minute, that there are different schools with very different viewpoints. So in the first half of the 18th century, electricity was a phenomenon that was not understood. Right? People just had a few phenomena. They knew it's different from gravitation, it's something else, but they didn't understand very much. And you know, the phenomena there of static electricity, you may remember, I hope at least from high school, if you have a glass rod and you rub it, and then you have little pieces of paper, then it may attract the pieces of paper. Right? This is static electricity. You may remember that. Right? Or you have different materials, and then different things happen, then suddenly the things have not attraction, but they move away from each other, and you have these phenomena. These are described somehow by static electricity, right? By static in our modern terms, that somehow the little pieces then of paper or whatever, they have an electric charge, and therefore they attract each other, or they repel each other, right? But people didn't have the concept of electric charge in the early 18th century. They didn't know that. That was an invention that came later. Now, people saw these phenomena that I just very quickly described to you, and there were very different schools. And I'm describing you now the viewpoints of 3 different schools, such that you get a feeling for how these different viewpoints could look like. Electrostatic attraction, you know, that the things attract itself, or that electrostatic attraction and the frictional generation of electricity were seen as fundamental by one of the schools. You know, the frictional generation of electricity, that is when you rub your glass stick, say, I think on cat fur. That's sometimes used. It's very effective, right? You take the glass stick, you rub it on cat fur, and then you go to pieces of paper, and then it attracts the pieces of paper, right? That's the phenomenon. So people observed that and said, okay, the fundamental phenomena for this very strange, it wasn't called electricity at that time, for this very strange phenomena, the fundamental phenomena is the electrostatic attraction, namely that then the pieces of paper are attracted to the glass rod, for instance, and the frictional generation of electricity. Right? They thought this is fundamental. There is another phenomenon, namely the phenomenon of electrostatic repulsion. Right? The two things with the same, as we describe it, with the same charge, repel each other. Right? And people thought, that's not a fundamental phenomenon of electricity. They didn't know. For us, of course, we know attraction is as good as repulsion, because it's the same sort of phenomenon, because we have two different sorts of charges. But 2 different sorts of charges was discovered much later. Right? That wasn't in the beginning. In the beginning, people just saw the phenomena. Right? They saw the glass rod, and then the pieces of paper. Of course, they didn't use our paper because they didn't have that sort of paper, but little particles, whatever they were, and they were dancing around, and there was attraction and repulsion. And one school decided, well, the fundamental phenomena for electricity that have to be explained somehow is really this electrostatic attraction and the frictional generation of electricity. This is the goal. And the other one, that from time to time you also have this repulsion, people thought, that's not important. Right? That's not fundamental. But what's really fundamental, you take the rod, you rub it, and then you get this attraction, and that's it. That's the main phenomenon. Now, this is, of course, quite a legitimate point of view if you don't know anything else. But these phenomena, you say, look, these are the fundamental phenomena that I observe. There is something else sometimes going on, but that's not fundamental. Right? It's a side effect of sorts, and we don't understand it really. Okay? That's one of the schools. Now, here's a different school. The other school said, no, attraction and repulsion are equally fundamental. So, if we want to understand electricity, we have at the same time to understand attraction and repulsion. It's completely symmetrical. And that's, of course, a very different point of view, right? They don't concentrate on this rubbing. They say, whatever that rubbing is, this is, so to speak, a precondition, but it's not fundamental for the understanding of electricity. What's fundamental for the understanding of electricity is that we have both attraction and repulsion. And we must concentrate on getting this symmetry between attraction and repulsion, which is, of course, a very different point of view. Again, if you don't know much about electricity, that's equally legitimate. And you may say, yes, that's also an extremely good starting point. Or from our point of view, we'd say this is the better starting point than this one, because understanding the frictional generation of electricity is much harder than simply understanding what is the basic thing happening in electricity, namely attraction of unequal charges and unequal sign, and repulsion if they have equal sign. That's our theory today, but they didn't know that, right? So, and here was a third school. They didn't really care very much about attraction and repulsion, but they had discovered the phenomenon of conduction, currents. And they said, look, all this attraction and repulsion business and also this frictional generation is fine, but it's not at the center of what electricity is. And they worked with an analogy, or not even, no, it was not an analogy. They believed electricity is a fluid. Literally a fluid, like water. Right? And they said, that's the fundamental thing. We discovered with these phenomena a certain fluid. And what we have to understand is the properties of that fluid. And that's the fundamental aim of electricity research. This other stuff, attraction and repulsion, will come later. That's not our point of view. But the point of view is we've discovered a new fluid, and if we want to understand this fluid, we must know the properties of that fluid, which is, of course, again, a very different point of view. And that is the characteristic situation in pre-normal science, that you have certain phenomena, and you start developing a certain viewpoint about, for instance, the importance of phenomena, and about the fundamentality of certain ideas. And there you may differ wildly, right? Really deep differences. And it's very difficult if you look at that, and if you look at the phenomena that were known, that I quickly described to you, it's very difficult to make a decision here. What is the right point of view? They can't be all right somehow, they're different. And it was these schools that were competing in this phase of pre-normal science that I described abstractly in the following way: a scientific practice which is not very structured, in which various schools compete. It is not very structured in the sense that these people do very different things. They follow very different lines of thoughts. They're developing very different sorts of experiments. If you say, in this school, you do not develop special experiments in order to study repulsion. Because you say, no, wait, repulsion is a secondary effect. That's not that important. We don't want to study this. We want to study, for instance, more precisely, the connection between the frictional generation of electricity and electrostatic attraction. That is fundamental, right? This must be our main focus. And don't develop experiments that tell you more about electrostatic repulsion. It would be a diversion. It would lead nowhere, right? Because it's not fundamental. And we must first understand the fundamental stuff. Whereas these people from the third school here, they will develop experiments and think about that. How can we discover more and know more about the properties of that strange fluid? For instance, does this fluid have a weight? Right? How heavy is it? That would be, of course, a question that's quite natural for them to ask about the weight of this electric fluid. Whereas the question of the weight of an electric fluid for these people doesn't exist at all. They wouldn't understand it. They say, what are you talking about? A fluid? I'm sorry. What we see is attraction and repulsion, and the point is understanding why is there both attraction and repulsion, and they have the same level of fundamentality, right? Again, in contrast with this school that says, no, wait a minute, no. You must understand this friction business of generating electricity. That's fundamental for an understanding of electricity. So that's a very typical example, therefore I choose it, of course, to get acquainted with that phase of prenormal science, where you have these different schools with these different points of view. And as I said, they are completely legitimate if you think about it. If you just know these phenomena and you start thinking about a deeper law behind this phenomena, a deeper understanding of these phenomena, of course, these three different viewpoints are all plausible. And if you say, okay, I find this one most attractive, so I do my research here, and therefore I will make investigations in attraction and repulsion and compare the two and look at them, have they equal strength or different strength or whatever you do then. Then you are on a research trajectory, on a research program that is of course different from these. And therefore the whole field of electrical research is somehow structured into different schools. And these people ask different questions and make different experiments and may even disagree whether a certain phenomenon belongs to electricity or does not belong to electricity. Right? And this is, of course, a very difficult situation for them to communicate and make progress here. Now, that is how most of the sciences we know of have started. The only field where we don't really know that phase is astronomy, because it's so old. In astronomy, we don't know the phase of prenormal science, because everything we know from the sources in astronomy is that people did have already a certain understanding and a certain consensus, say in ancient Greece, or in the other cultures. There seems to have been a certain consensus, and we don't know what the phase looked like in astronomy. But in the other natural sciences like chemistry or in all different fields of physics, we know of these prenormal phases which have these characteristics of these different schools talking, having different points of view. Okay. So that looks, in a sense, a little less than science, real science, because in real science, what we are used to say in physics is, of course, that, or engineering, we have a consensus, right, about the fundamentals. If you look at engineering disciplines, there's typically a basic consensus. There are differences concerning smaller things, but certainly there is a basic consensus about what the field is and what the problems are and what the fundamental theories are. But that's not the case, and of course you can imagine that if you have a field with a consensus, that when you go back, that the consensus wasn't there from the very beginning, because this consensus had to be formed. And the phase before the consensus, that is prenormal science. Okay? So, let me see whether I can continue from here. Mechanically, I can. All right. Okay, is this clear and plausible, this form of prenormal science? It must be plausible, it can't be more, because I only give you one example. Now the question is, how come, or how can it possibly be happening that people move out of this competition of schools? And that is the transition to normal science, what is called normal science, of which you don't know yet what it is exactly. And first I give you a name. The transition to normal science is called the maturation of the field. It becomes mature. Mature in the sense not like an apple, well, also like an apple, that it's, has a full form then, or a mature biological item, meaning it has then all the capabilities that usually connected with that specific form of life. In this particular case, the maturity of a science means that it resembles what we usually think, today at least, what a developed basic natural science looks like. And a fundamental characteristic of a basic natural science that has become mature is that there is a sort of consensus among the specialists, right? That's different from the social sciences, because in the social sciences, even among the specialists, there are typically differences about fundamental questions. But in the natural sciences, they are somehow different, and therefore also sometimes a model for the social sciences. A characteristic point is that, not always, but sometimes the practitioners of a natural science, of a specific field, have a certain consensus, right? They agree on the fundamentals of the field. And that is a characteristic of normal science, to which I come back in great detail. But here we look first at the transition. We have in pre-normal science different schools. They are in competition. There are different viewpoints. And now we get a transition phase called the maturation to normal science, and we have to look how that can happen. Now, the source of this maturation, of this leaving the stage of pre-normal science, is that one of the schools produces an extraordinary convincing solution to some of the fundamental problems of the field, such that the members of the other schools join this school. Okay? We have these different schools, say, of electricity, and they deal with the problems of electricity, trying to understand attraction and repulsion and the generation, frictional generation of electricity. And now imagine the following thing, that these people know about these different phenomena, and now one of the schools develops a solution that is extremely convincing, such that people get the feeling, oh, we in this school, have solved one of the fundamental problems of the field. And the people from the other schools observing that then say, oh, they have a fundamental solution, we don't. Why don't we join the others? Right? It is just by developing such an extraordinarily convincing solution to some of the fundamental problems that the members of the other schools say, look, there are much more chances in this school than in our school. We didn't move much, right? We didn't solve any of the fundamental problems, but they did. I think their school is the better one. Why don't we join them? Okay? That is what historically has happened again and again and again, right? From this pre-normal phase with these competing schools, sometimes it took a very long time, sometimes it didn't take such a long time, maybe a few decades. Well, a few decades, quite a long time if you look at your own life. But it may happen then that one of the schools is really so successful such that the other schools join that school. The fundamentality or the extraordinary character or the convincing character of this solution must be such that the fundamentals of the field now seem to be clear, such that further research can be built upon them. That's the idea. So it's not just a very nice solution to a problem and then you say, finish, okay, where do we go next? No, it's a fundamental solution such that you think, oh, we can build further research on that. We can continue from here, and we have an avenue of further research. We can hope that we can develop interesting problems on that basis, right? So it's a promise for fruitful further research, and that's most important. That's why it's interesting to join the school. It's not interesting to join the school because they were so good in the past, right? That doesn't help you for your career, for your future as a scientist. But the point is there must be a strong promise of good research, fruitful research, where you can excel and show your abilities and capabilities of doing research, and that's the promise of this extraordinary solution. The fundamentals now seem to be clear, and further research can be built upon them, and that makes the attractiveness of that what happens in this school. Again, you may say, well, why should that happen? Well, I can't tell you really, but I can tell you that in the history of science, that is what happened again and again. And that is how modern science formed. That out of these phases of pre-normal science, one of these schools typically, after a while, short or long, they found a solution to some of the fundamental problems with exactly these characteristics, extremely attractive for the other schools, such that the members of the other schools then came to this school. Now, when I say that the solution was extraordinary and attractive, that means an evaluation. I'm using values. I'm not just describing what the details were, but I'm saying I'm evaluating it as especially positive, right? I'm saying it's attractive. And you can, whenever you say something is attractive, or you value it as good, attractive, or extraordinary, there are certain values in place, okay? So if you value a certain university as especially good, then you have certain values. For instance, you value research as very important, or teaching especially important, or especially courses, say in horticulture science is especially good or important. And then you choose it, right, on the basis of values. Or if you find a certain partner of the other sex or of the same sex, whatever your preferences are, if you find him or her especially attractive, you value certain things. She is especially beautiful, or she's especially rich, or she's got especially nice hair, or whatever it is. You have values. You're applying values. Or beautiful eyes, or whatever it is, right? But you're applying values. Whenever you make such choices, you're applying values. And why I'm saying this? Well, for entertainment only. No, not for entertainment only, but in order to apply that here. So when people say this solution of this school is extraordinary, attractive, the question may be on the basis of which values? What is the basis from which they evaluate this as especially attractive? And here what we have in scientific communities is so-called scientific values. And that means here the decision for a theory associated with the outstanding solution is based on a set of scientific values. And the scientific values that are relevant here, I'm giving you some sort of, not a finite, not a definite description, but I'm just hinting at some of these values. They include scope, accuracy, predictive power, consistency, and fruitfulness. And I'll tell you a little more what these values mean. Okay, remember, the one school develops a solution to fundamental problems, and this solution is always connected with some theoretical elements. Say, for instance, yes, electricity is a fluid with such and such properties, and therefore we can explain a broad range of electrical phenomena. Now, the scope of a theory means the range of possible applications. And the more possible applications you have, the better a theory is, because it's more useful. You can do more predictions, you can do more explanations, because you can apply it to more and more phenomena. So one of the aspects what makes a theory attractive is not the color of its hair, because theories usually don't have hair, but they have scope, you know, the scope of possible applications. And that is something you look at when you have a choice between theories. This one is a very narrow theory, only covers very few phenomena, and the other one covers many phenomena, so you take that one that has a broad scope. Another one is, of course, the accuracy, the quantitative accuracy, for instance, of the predictions. If a theory that predicts more accurate, of course, it's a better theory. Or if it explains more accurately, of course, it's a better theory. Another one is here predictive power. A theory that has more predictive power, can predict more phenomena, is of course a better theory. That's what you want from theories. They should predict, as I told you in the first or second session. And the consistency, a theory that's consistent, right, where all the parts somehow cohere and are consistent with each other, is much nicer than a theory that consists of different parts without connections or even in contradiction. And you just say, yeah, I have to use it, I'm sorry, it's not consistent, but that's the best I have. So you prefer a theory that's consistent. And that's a more general, again, description, a theory that's more fruitful, meaning in directing your future research, what you should do next, is of course a better theory than a theory that's less fruitful. So these are the values, and they are very important, quite apart from paradigm theory. The scientific values, these are the typical scientific values by which scientists, and that includes us as well, by which scientists evaluate theories, right? These are the values that are used here: scope, accuracy, predictive power, consistency, and fruitfulness, mainly. And they form the basis on which the accomplishment of one of the schools, this extraordinary convincing solutions, is judged. That's the basis for the judgment, right? So it's completely transparent what's happening there. I mean, the scientists run around with these values and they say, we look for a theory that has these properties: broad scope, accurate, predictive power, consistency, and it's got to be very fruitful. And then one school develops a certain solution for a fundamental problem, and they say, here's our theory that's connected with it, and then you look at the theory, and then you discover it's much more broad, it's much broader, more accurate, has more predictive power, and so on and so forth, than the competitors, and then you say that's the better theory. That's what I'm going to work with, especially because of this one here, of the fruitfulness. Because as a scientist, you want to work with a theory, right? That's the whole idea of it. You want to work with a theory and do something with it, develop it, apply it, whatever it is, and therefore you look for theories that are as fruitful as possible. That's your whole job as a scientist, right? Therefore, it's completely transparent why scientists then leave their own school and join the other school that developed a theory with these properties and that is able to solve one of the fundamental problems of the field. That's then convincing, and then people start to join that school. And then you'll see they will, in the end of that process, they belong more or less to the same school. Okay? I'll give you an example. Okay, is that in the abstract, is that somewhat clear? Okay, more or less? Okay. I'll give you an example and then we'll have the break. No, I have the break right now, and then we come to Bohr's atomic model as an example. 10 minutes break.